Hello, everyone. I'm here to talk about a few of my experiences that I hope you'll find interesting. I work as a CTO for a French company called Local. It's a small company, less than 25 people, and our customers are mostly retailers. They need to decide for their entire catalog how many units to order from the suppliers, when they should be delivered, and to which store or warehouse. So every week you're looking at tens of thousands of small supply chain decisions. And humans are very bad at this kind of stuff, so Locat builds software that makes those decisions for you. We forecast all possible futures and then pick a strategy that optimizes your profits, your availability, or something else. 4 years ago, we created our own programming language called Envision. It's purely internal, it's only used at Locat, and it borrows ideas from Python and SQL and R and some bits of Julia. And today we have more team members, using Envision than C#, F#, and TypeScript combined. So I wanted to talk about the language, its features, and how we built it, and so on, but this is not that talk. This talk is about helping you guys create your own programming language if you want to. So, first question, why did we build our own language? This usually seems like a bad idea, especially for a small team like ours. So, our customers all have some weird details in the supply chains that our software needs to handle. And in the beginning, we had options and configuration screens. I'm going to give you some examples. Try to imagine what those screens would have looked like. So first, we had a customer that needs to add 1 week to delivery times to their warehouse in Russia, but only for items that need to go through customs. Another customer has suppliers that are not available around Chinese New Year's Day. In the novelty t-shirt business, your suppliers won't let you order less than a certain quantity for each t-shirt fabric and for each t-shirt print. But you can mix fabrics and prints any way you like as long as you stay above those quantities. And what about the consequences of ordering too much? Something like office supplies will just stick around until you sell them, but unsold fresh food spoils and unsold clothing goes out of fashion and needs to be sold at a discount. And I could go on forever. Like, you will run out of checkboxes and radio buttons and configuration pages before you can handle all the insanity that customers can throw at you. So we decided to write a small bit of custom code for each client. Now, of course, most code, especially the clever parts, are written once and then used everywhere. But every client needs some customization, and so we needed a language that's good at writing many small custom scripts. Why not Python then? Well, Python is too powerful. Client comes in with some outrageously weird or unusual demands, but all you have to do is import a package, implement an algorithm, and the client is happy. That's the power of Python, right? And then, 10 months later, the client uploads some data that just happens to summon an elder abomination in your code. And you're on holidays, so your team has to deal with it. And they've never heard about that package. And they're not sure that algorithm is doing what it should be doing. And is that really an infinite loop or just an exponential time complexity that has never been called in a large data set before? And there's so much data now that it will only run on the production cluster. And if you want to run the script again, you'll have to undo all the changes it does to the database every single time. So that's the problem with client-specific code. It's written under pressure to deliver something, so you tend to cut corners and skip documentation and break your own rules. And you won't get a chance to go back and fix it later, or even read it, unless something goes wrong. And it's... Hello? And it's not tested. Of course not. My slides are stuck. Okay, let's do it live. Oh, cool. So we designed Envision so that despite the unavoidable problems I just mentioned, writing client-specific code does not turn into a maintenance nightmare. First, by limiting the power of the language, we can provide guarantees about what a script can or cannot do, even if you break the rules. First, we're not Turing complete. Just like SQL, we have no for, no while, no recursion, only for each. So we cannot have infinite loops, intentional or not. Then, every script runs as a transaction. It takes a snapshot of its input when it starts, and then commits all of its outputs at the end. This means many race conditions are eliminated, and if you want to run a script without its side effects, all you have to do is skip the commit phase. Run the same script on the same data, and you get the same result. And this is a very useful property for debugging, and it's very easy to lose it. All you have to do is import a machine learning package and forget to initialize the random seed. Is it back? It's not. And Envision will only run in our online environment. So this means we've kept a copy of every single script that was ever executed, along with its input and output. And this is amazing for forensics. We can actually go back in time and find the exact moment when a script broke, even if it was caused by data change instead of a code change. And finally, we have static analysis. We can actually find errors in branches that are not executed yet, because we don't like surprises in production. We also did some crazy things with caching and diffs. Like if you change one line in a script, then we're going to find out exactly what needs to be executed again. This usually means running in 5 seconds instead of 1 hour. And since you can disable side effects, you can do this in production with actual production data. So this makes it very easy to explore what a script is doing. And finally, we get all the benefits of a domain-specific language. We can adapt the syntax and semantics to our specific needs instead of them being general purpose. There, caught up. Okay, so this is how you read files in Envision. Now, this will take the items file and load it into the items table, but that's not all. Since we have type inference, we know the name and type of each column that we need to find in this file. So we can parse it ahead of time and generate warnings. And then we're going to take a column named ID and use that as the primary key, eliminating any duplicates, again with warnings. And we're going to do the same for the orders table, except this time ID is the foreign key, so we drop any orders that don't match an item in the items table. So this is useful to us. We actually save time by being able to rely on this behavior, and none of it appears in the actual code. It's all driven by convention that would not make sense in a general purpose language. So all of this is why we created our own language. Now on to the interesting part, which is how. What are the tips? What are the lessons that we've learned over 4 years about how to create your own language as a small team? First, you need a parser to turn a script, which is a bunch of text, into something that your compiler can manipulate. Now, you don't need me to tell you this. There's plenty of tools and techniques and libraries that you can use to do that. My lesson is this. You need something called an LR1 grammar. Look it up. My point is, this is a subset of the TypeScript syntax. So an expression is a binary operation or a function call or an object literal or a fat arrow function with a body that's either an expression or a block of statements. So you can implement this with a recursive descent parser or with parser combinators. Why do you need an LR1 parser? This is what statements look like, by the way. Any ideas? Yeah, so if you've used TypeScript before, you should know this. Is this a function that returns an object with a field called ABC, or is this a function that returns nothing and contains a useless label called ABC? And both are valid for that grammar. So this is an ambiguity, and you want to know about it as soon as possible during the design of your language, because you want to decide what the correct choice is, and you want to make sure that the parser picks the right choice every single time. With a recursive descent parser or with parser combinators, well, you won't find about this until it's in production. But with the tool that turns your LR1 grammar into a parser, well, the good news is it will detect this ambiguity. It will say something obscene like shift-reduce conflict, but you can interpret that and fix the problem. And finding it in production is usually good news, because the worst that can happen is that you change the parser in some way, And all of a sudden, it starts picking the other choice. And you didn't know about it. So now you have scripts broken in production and you have no idea why, and they haven't been touched in months. I can see two cases where you don't need an LR1 grammar. One is you have a language that's so important that you have a team and community large enough to detect those issues ahead of time. Or you're implementing a grammar that was designed by someone else, so you have all the ambiguities pointed at you. Picking a host language. So what's a host language? If you have an interpreted language, then the host language is the language that the virtual machine is written in. Envision is an interpreted language, and our host language is C#. If you have a compiled language, then the host language is the language that's generated by the compiler. It doesn't have to be machine code. You could generate C code and use GCC to turn it into an executable, or you could generate JavaScript or anything else. The choice of a host language has important long-term consequences, so you need to make sure you pick it for the right reasons. First, performance. You probably won't be able to run faster than the host language itself, so if this is important, pay attention. Then, do you have access to a garbage collector, or do you have to implement your own memory management? And does it matter? Do you have access to the libraries useful for your projects? For instance, regular expressions, hash tables, and Unicode support, and so on. And finally, the tools. You probably won't get a chance to implement good debuggers or good profilers for your own language. So for a long period of time, you'll have to rely on those provided by your host language. Again, that's a good criteria for picking one. Lesson 3, keep all your code in one place. You can do this because it's your own language, so all the code that has ever been written has been written by you. We keep all the code in the database of our web application, but you can keep it in Git if you want to, all in one place. That's important because you will mess up the design of your language. Miss something essential, or maybe something like that seemed like a good idea will turn out to be very bad later on. The important thing is you need a way out. You cannot live with your past mistakes forever, and you cannot afford to freeze the design of your language because you're afraid of making mistakes. Early during the design of Envision, we decided that string equality would be case insensitive. And it was a good idea at the time because, well, we work with human-generated data, so case tends to be a mess. Still, at some point, we needed case-sensitive comparison. So we could have added a triple equals operator. We wouldn't be the first language to do that, but that would be a very bad idea because every single person who joins our team is going to have to learn a new language. So we want to keep the footnotes and the surprises to a minimum. So what we did instead was we broke the API. We decided that from now on, string equality would be case sensitive. And we added a new operator for case insensitive comparisons. And obviously this broke every single script that we had ever written. So the next step was to do a global search and replace over the entire code base. We replaced the equality sign so that we could restore the previous behavior. And we could do this because we had all the code. We weren't afraid of having a bit of code somewhere that would end up in production without having been changed. So this kind of global search and replace is the only way you can get rid of backwards compatibility problems. It will let you move fast without breaking things, and you end up with a language that's more powerful and cleaner at the same time. Lesson 4, static analysis. You will need it. Every single tool that you create around your language will get a lot weaker if you do not have static analysis. For instance, when we did the string replacement, well, we only replaced the operator for text, not for numbers, not for dates, and we could do this because we could compile every single script and determine the type of each expression. Now, this doesn't mean you have to implement complete, complex static analysis from day one. All you have to do is make sure that when you will need it, it will not be impossible. So obviously, you shouldn't add features that prevent static analysis, and something like being able to execute any piece of string as a script is a fairly obvious offender, but even something like a substring function that changes behavior when passed negative arguments is a bad idea. Use two functions instead. Lesson 5, keep a small API. So what's the API? It's everything or behavior that users rely on. And you want to keep it small because that makes it easier to explain, and it makes it easier to change the implementation to make it cleaner or faster or anything. But how do you do that? I mean, you can just write your API on a piece of paper and be done with it. It's not what people can rely on, it's what they do rely on. So if they use something that's outside the API and start relying on that behavior, a piece of paper won't save you. So, quick aside, adding the empty list to the number 1. What does this do in JavaScript? It returns the string 1. So this is part of the API. So every implementation has to do it, and this is what you have to teach every JavaScript developer. And there's actually a way to explain this while making sense. Moving on. Python throws an exception. And that's easier to explain. But this is still part of the API. I can promise you that someone somewhere, for a very naughty reason, relies on this exception being thrown. Now, OCaml says, it says nothing. Like, it won't compile. You cannot have an OCaml program which executes this. So what I'm getting at is the difference between failed and broken. Failure is part of the API. You can expect it. You can rely on it. Something like divide by 0 will always fail. On the opposite, brokenness is outside of the API. Someone wrote nonsense. Someone broke the compiler. Something happened to the virtual machine. You cannot expect brokenness. You cannot react to it. There's no broken exception that you can catch to fall back on your feet. And you want to emphasize the difference between failed and broken. In Envision, when you break something, well, first of all, it usually won't compile. But even if it does, because it's broken at runtime, it stops. There's no output. There's no nothing. You get nothing out of it. Because we want to make it clear that it's not acceptable or even useful to have broken behavior in production. And sometimes people come to me and say, oh, maybe it should still... No. It's broken. You get nothing out of it. And that's final. Another thing about APIs. You know C# is a host language. So how do you call a function from the host language? Well, usually what you'd see is something like an extern or import keyword that fetches a function by name for the host language. But this is a very bad idea because it adds every single function in the host language to the API. So instead what we do is we add a little bit of boilerplate to a function in C# because we deem it worthy of being part of the standard library of Envision. Lesson 6. You cannot dog food documentation. Like, your compiler team, very clever guys. They know everything about every feature. They know how it works, how it should be used, and how it was designed. They do not know how hard it is to understand by a normal human. So you end up with a language that's very good and no one understands it. So what can you do? Well, before you implement a feature, go out and teach. Like, write down the documentation and show it to other people. You're not asking for feedback. You're trying to see if they understand. Do a pop quiz. If they don't understand, write the documentation again. If they still don't understand, change the feature. It won't work. And another thing, you need people who love to complain because it's an internal language. People are paid to use it. Of course, they expect it to be bad for plenty of reasons, many of which you are already aware of. But you need someone who loves to complain anyway, just in case there's a quick fix or a quick win somewhere that you might have missed and that they will gladly point out. Lesson 7, leave language design to the professionals. Everyone who's using a language has clever ideas about how it should be improved or fixed, and so on. And those suggestions are usually very bad. So you want to ignore them. And you want to try and find what problem they're trying to solve. And then find a way to fix that problem without breaking anything else, because that's where most suggestions go wrong. Those people, they aren't stupid. Like, they know how to solve the problem, just that there's some long-term, far-away chain of consequences that break something completely unrelated that they didn't think of. And that's the job of the compiler team, is to follow the trail and make sure that it doesn't break any other feature, make sure that it doesn't break anything not yet implemented but already on the roadmap, and it doesn't break anything fundamental to the design of the language, such as static analysis or being deterministic. And another thing, make sure that the head of language design actually has the final say in matters of language design. This sounds obvious, but it's hard to keep a clear direction in the face of interference from the CTO or from other engineering leads. Lesson 8, which is probably the most important one, know how to debug your compiler. You've been taught all your life, if you have a bug, the problem is in your code, not in the compiler. I mean, compilers don't have bugs, and even if they did, you wouldn't be the one who find them. But well, this time it's your language, so the compiler is also your code. So you need to be very good at answering the question, is it the script or is it the compiler? And every week I get someone in my office saying, my script is doing something weird, can you take a look? And usually I teach them something they didn't know about the language or about spelling things correctly. But sometimes there's a bug in the compiler. Okay, so now you got a bug in the compiler. What do you do? First, reproduction. A compiler is a very complex program, so you cannot afford to just stare at code for hours on end hoping to understand why something happens. You need it to happen before your eyes. In Envision, I can, in 5 seconds, get any run from production and execute it again on my machine. Same data, same code, exactly the same thing. And this took a lot of effort to get working, but it was so worth it. Once you get it running, well, you have to debug it. With a normal program, you have code processing data. So you just work backwards from the place where the data is wrong, asking yourself the question, is it right? Is it right? Is it right? Until it is. With a compiler, well, it's code that generates code that processes data. So the question you need to answer is the generated code correct? And you can answer this by answering the question, is the data correct? But that takes hours. So you need to be very, very good at answering the question, at knowing what the generated code should be. And well, to do this, it's all on a human side. It's training. You need to ask questions from your team, and you need to have seminars about how the compiler works, and you need to have concrete examples about how the compiler deals with specific language features. And white papers and specifications outside of the code, so you know whether the code is wrong or the specification is wrong. So all of this is training. Debugging a compiler is skill. It's a job. You have to train people into it. And that actually takes some time. You have to make time for it in your team. Lesson 9, automated testing. When you break something, it hurts a lot of people because the compiler is a critical component in all the scripts that you use. So you want to make sure before every release that nothing is broken. I don't like unit tests a lot in compilers because the internals tend to change a lot. So if you want to unit test some stable components, go ahead. But every month we throw away entire units because they're not used anymore and the unit tests go away with them. Instead, what you should be testing the most is the stable API, which is the language itself. It's what I call script tests. You have a small script and a small input, and you check that the output is exactly what it should be. And you have thousands of these, and they run very fast, and they check everything that might happen in the language. And when you have a bug, you can try to reproduce it, creating a new test. And finally, regression checking. Those small toy tests, they don't actually check everything. Production, the scripts are bigger, the data is bigger. You have weird stuff happening that you wouldn't even think of because the client uploaded some insane data himself. Like one time we had a value that was 8 megabytes of white space. How do you deal with that? And so we release Envision, a new version, every Tuesday. So every Monday we pick at random 1,000 scripts that were recently executed and run them again on the new compiler architecture and make sure that they have the same results to the bytes. And if they don't, we check whether there's a good reason. For instance, we fixed something, so now the result is correct when it wasn't before. And this is how we guarantee that we don't break everything, because a rollback on a compiler, especially when you added a new feature, is extremely painful. Final lesson, documentation. With a mainstream language, you have tutorials and books and people who already know about the language trying to join your team. When it's in your own language, you don't have that benefit. You have to do everything yourself. So I'll state the obvious. You need training sessions. You need a few months when a person joins with pair programming and reviews and so on. But how can the language itself help? It can help passively by being easy to understand, not having too much complex elements in it, no footnotes, no surprises. but it can also help actively. Like with Envision, you can actually easily explore. You can go to production and clone a script, disable side effects, and it's a sandbox. And you can do anything. You can find out how we implemented details for our biggest or most complex or oldest customers. And if you want to try out a new function, well, you can just plug some data set and try working with it and see how it actually works with the function you're trying to use. Test how long it takes, and so on. So we actually encourage people to explore through the design of the language itself. And another thing, when you have something broken in your code, how do you share it with someone else to ask them a question? Like, you can't commit broken code. So we allow you to create a clone project that's broken by design, and you have a new URL that you can give to someone else and ask them, well, what's going on? I have a bug in this. Do you know why? And if it's sent to me, it's usually because it's a bug in the compiler. So I can clone it myself and try to toy with it to find out whether it's actual compiler bug or just someone messing up. Finally, if you're serious about creating your own programming language, then you have to accept that you will have, for years to come, a compiler team working full-time on it. And if you actually make the effort of hiring a team of compiler experts, then everything that I've said will probably feel obvious to you. But still, I really hope it works out for you if you decide to do it, because it's a really beautiful job. So thank you all for your attention.